Alright, now for this second part of Unit 6 Lab, we will be migrating our program onto the GPU. Notice that I'm using a dimension, and here I'm going to make it 512, and I'll talk about this a little bit later with this version that I'm writing, why we're kind of limited to smaller numbers. And I'll show you what needs to be migrated to the GPU side. Obviously, my kernel needs to be migrated to the GPU. So this CPU kernel, the serialized kernel that I wrote here, that takes the data pointer for my image, and then goes through every pixel in each column, in each row, and calculate the location of that pixel in the data pointer array of my image, then calculates the Julia value for it and sets the color of that pixel in the data pointer of my image to 255 times Julia value. And remember, Julia value would be 0 or 1. So obviously this needs to go to the GPU. Now, we haven't really talked about the memory layout in the GPU so far yet, but this should give us a very good startup to decide what parts of this code would run on CPU and what parts would run on GPU, and we'll see these in more detail. Apparently, the CPU kernel, when I rewrite it in terms of my GPU kernel, this would be the function that operates on the device. So I rewrite this function, call it GPU kernel, tag it as global, and it runs. It will basically run on the device. There's one slight problem though. If you look at the Julia value calculation, it is calling a function, and this function, I called it CPU Julia. The problem is that from my device, I won't be able to make any callbacks to the CPU functionalities. So I need to rewrite my Julia function, which is going to be this function up here. And to rewrite this function, I would have to write it, and the calculation would practically be the same. The only difference is that I would have to tag my GPU version of this function as a device function as well. Now, another problem here is when I tag this and I run it on my device, there is a slight problem, and that is these functions, these variables, A and C, these complex variables that I manually defined as CPU complex, these are going to be created on my host. So I need to also have a mechanism to tell my GPU what a complex number A and a complex number C would look like. So I need to rewrite my complex structure here. So I'm going to call this GPU complex, make it a structure, and then tag all of its data component and function components to be also device functions. Because as a part of creating this CPU complex, it's going to have to create code that is hosted in CPU when I'm using my Julia version of the function on the device. It will not have access to the CPU structures, so I would have to redo my structure on the device as well. So we're going to take this step by step and run it and see how it works. Okay, so first I'm going to create a GPU complex structure, and I'm going to make this structure basically have device functionalities. So let's go down here and let's tag these functions and functionalities as CPU side functionalities, and then let's create another set of functions here, GPU side functionalities. So I need to create a structure that hosts the data that I will be working with on the GPU. So struct, and the amazing part of this is that of CUDA programming is that a lot of this is just standard C, so the syntax should be fairly familiar. So I'm going to create a structure and call it CUDA complex or cuComplex. And then the cuComplex will have a local variable float for its real part, just like my CPU, and an I for its imaginary part. Then the functions that I create, the constructor, the function to calculate its magnitude, and the two functions that would calculate the result, or rather the operators multiply and the operators plus. These would need to be GPU side functions, because remember, you cannot make direct callbacks from GPU or your device to the host and vice versa. Your only means of callback and communication between device and host is your memory layout. So how am I going to do that? The way to define a function on GPU is fairly easy. The only thing you need to do is to tag it to be a device function. And you do that with underscore underscore device underscore underscore. Any function that you tag with this keyword is going to be a device function. So I'm going to make my cuComplex constructor as a float A, float B. That will make the real part be parameter A and the imaginary part be parameter B. Next function that I wrote was the calculation of magnitude, and I will tag that function also as a device function, mag2, which will return r times r plus I times I. Next function that I will need to write is going to be and it has to return a float value. Next function that I'm going to have to write is, or rather overload, is overloading the star operator and overloading the add operator. Same thing, tag them as device, and they would return CUDA complex variables. The function that I'm overloading is going to be operator constant cuComplex reference A. And what does this return? It's going to return a cuComplex whose real part is r times a dot r minus I times a dot I, and its imaginary part is going to be I times a dot r plus I times a dot r. So this is the operator multiply that I overload for my CUDA complex data structure. Then I'm going to also tag cuComplex operator plus and this operator also returns a data of the type cuComplex that would have a real part being the sum of the two real parts and the imaginary part being the sum of the two imaginary parts. So then again, to go over this functionality, the structure cuComplex, this is a device structure. So since this is a device structure, we need to tag functions as device functions. So this is the device side constructor. This is my device side magnitude, device side star, and device side plus operator that I overloaded. So basically, you're going to have to, for any abstract data type that you create, functions and classes and structures and unions, if you have functions with them, if you have methods with them, the methods need to be tagged device. The reason is that, see, when I define this complex and I create a variable of type complex on the device, these float R, float I will be local variables that would be hosted within the thread on my GPU. If you call complex, the function would have to also be on the GPU. So that's why I put the complex, mag2, and operators plus and star on the device, so that I'll be able to invoke these functions on the device side data. Okay, so this is wonderful. I already created my CUDA complex or complex data structure that I will be able to work with on my device. Then I would have to go and create. So now I have this device, and so I need to go and create my Julia calculation that takes two values, x and y, as the location of my pixel, and calculate my my Julia set value for each of these pixels. Now, the only problem, as I mentioned, is that if this function is on CPU and I have my CUDA complex operators on GPU, they will not be able to call the CPU Julia set. So I need to basically redo this process and make it a GPU process. It's, again, incredibly simple. My GPU side code for Julia set is going to be identical to the CPU side, with only one difference. The difference is that basically I'm going to call this GPU Julia, and also I tag this as a device function. So now my function GPU Julia will be created on my graphics card, and it'll run on my graphics card. The problem is I need to also make the complex numbers that I'm creating here graphics complexes. Those are the two. Remember, CPU complex was the one that we created for the CPU code in Unit 6 Lab Part 1. And in this unit, just a few minutes ago, I created complex on the GPU. So I'm going to basically create the complexes, complex variables on the GPU. So from this point on, function structure A and structure C, when they are created, they are going to be created on the GPU. Okay, so one last bit is, now that I have my CUDA Julia calculation or GPU Julia calculation, I'll need to go and write my GPU side kernel. The GPU side kernel is the meat of the matter here. Okay, so how am I going to do this? Let's switch to my whiteboard, and I'll show you what I'm going to create here. So basically, the idea, as I said, is that I'm going to have an image, and this image will have, essentially it's a black and white image, so it's going to have a bunch of pixels in X and Y. Okay, so it's going to be pixels Y and X dimension. For each of these pixels, let's say this guy, I'm going to call this X, Y. Now, in the CPU side code, I had two for loops. I went for Y and then for X, and then I calculated where offset is, which basically was easy. Was X plus Y times dimension, right? So if you have n, if you have dim number of these guys here, all you need to do is to just calculate how many you have in the rows. Actually, let's call this X and let's call this Y, to be true to our row major constituent. So you're going to basically add the location of x plus the location of y multiplied by the number of the dimension that you have. So number 0, 0 is going to be 0, number 0, 1 is going to be 1, 2, 3, and then so forth. And then this is going to be dim, and then dim plus 1, and dim plus 3, and then 2 dim, 3 dim, 4 dim, and so forth. So that's the CPU side code. What I'm going to do in my code here is I'm going to get rid of these two for loops. So to get rid of these two for loops on the GPU side, what I'm going to create one block per pixel with one thread. So I'm going to make one block which will have one thread per pixel. Okay, so if I do this, then I'm going to have basically a bunch of these blocks, kind of like this, with one thread each. And then associate each of these items, each of the pixels, to one of these threads, right? So block number 1 is going to work on pixel number 1. Block number 2 is going to work on pixel number 2. Block number 3, block number 4, and so on and so forth. So what's going to happen here, these blocks will have two dimensions. Block index.x and block index.y. And so this is going to represent my x directly, and this is going to represent my y. So my calculation is going to be fairly easy, especially if I use one thread per block, and each block will be basically responsible for calculating one unit of operation, which in my case, since I have a map operation, it's a straightforward map operation. One-to-one mapping. I have one thread in one block associated to one pixel. The next thread in the next block associated to the next pixel, and so on and so forth. So let's write this and see how it works. It's actually incredibly easy to write. So I need to create my global kernel, which is going to be a global function, and I call it GPU kernel. And this will take also a uchar pointer, and I call it D pointer because it's going to be in the device. Notice that the name of this D pointer doesn't really matter. The type matters because my as if you remember from the programming assignment part 1 in lab 6, the data values that are CV underscore 8 UC1, these are of the type unsigned char. So I'm going to pass now to my GPU kernel my image data, and that should be a pointer that is going to be an unsigned character. So now the meat of the matter here is going to be the calculation of my Julia value and writing that Julia value into my offset. So remember from the CPU side code here, I go for every x and every y, and then I calculate the offset as being x plus y times dim. Now, since in my calculation of my CUDA code, I have one block per x and y, then the x is going to be block index.x and the y is going to be block index.y. And then the dimension is going to be the block dimension, which is in CUDA is called grid dim.x. So and here is how it looks like. My x value is directly block index.x, my y value is directly block index.y, and I automatically got rid of two for loops in one step. So in this case, int x is going to be block index.x, and then int y is going to be block index.y. And of course, my dimension is going to be the size of the block, which is going to be grid dim dot x. The dimension in one row of my operation. So again, let me show you how it looks like. So each of these x and y values, is going to be equal to the number of block in x and the number of block, or the block number rather, in y. And then the dimension, how many of these I have, is going to be grid dim dot x. And the dimension in this long is going to be grid dim dot y. So to calculate my offset, I'm basically going to add x to y multiplied by the size of row. Now, the location of my data, or my block, or my pixel, is going to be an int offset, which is going to be x plus y times dim. Fairly easy to do. Now, finally, I'm going to calculate Julia value equal GPU Julia for x and y. And then I'm going to write this GPU value into the data pointer. So it's going to be d pointer at location offset is going to be 255 times Julia value that I calculated above. Okay, so wonderful. Now here is again to go over. This is my GPU side kernel. What I'm going to do is associate pixel in x with block at x, and then do the same thing. This associates pixel in y with block at y. This is the size of rows, and this is the location of each pixel x comma y, or each pixel or block, because each block has one thread, so that is a very easy thing to do. And this calculates the Julia value for x, y on GPU. And finally, this colors the pixel with black or white, depending on whether you've got your pixel inside or outside of the Julia boundary. Now, the last piece, which is technically speaking the first piece to do, is to take care of memory allocations. Now, let's get to this. How am I going to go and make my memory allocations in CUDA? Now, remember the steps that we talked about in Unit 5. You basically go on the CPU, allocate memory when you need to. Here, line 142 is exactly that, CPU side memory allocation or host side memory allocation. Step 2 is to go and declare and allocate memory on your GPU. It is incredibly easy to do. There are essentially 2 steps to it. Create a pointer, define a pointer, and allocate it on your GPU. To define a pointer, I'm going to basically, remember, since my data pointer for my image in this case is CV_8UC1, it's the unsigned char, I'm going to create an unsigned char pointer and I call it dptr. Actually, let's make this device_ptr, because then it just shows me that this is actually on the device. I mean, I remember by the name that it is allocated on the device. So how am I going to allocate this? I'm going to create a variable to hold my error. If there was any error with the declaration and creation of this variable, I call it CUDA. So I created CUDA error variable, and let's call it error. And then I'm going to call CUDA malloc. The CUDA malloc function basically takes it's basically a function that takes two pointers, actually one pointer, your device pointer, and the size, how much you want to allocate on it. So I'm going to create or pass the reference to my device pointer here, which is basically the pointer that I declared up here on line 144, and then the size, which is going to be equal to the size of my image. My image dot calls times my image dot rows, and this should calculate and allocate the number of bytes I need. Now, notice there's one thing that I didn't put here. See, here I've got how many columns is on my image and how many rows is in my image. That is how many pixels I have. Technically speaking, it would be ideal if I multiply it by size of ucat, because each unit in my data pointer on the device is exactly 1 byte. The size of ucat is going to be exactly equal to 1. But if you had like a CV_8UC3, that would be 3 bytes. So you basically would create that many rows times that many columns times that many bytes. If my allocation of my device pointer on the GPU is successful, CUDA malloc will return success. Otherwise, it will return an error. Then I can see out that error. So, for example, here, what I'm going to do is I'm going to go and see if error is not equal to CUDA success, then printf there was some error in memory allocation on CUDA. Okay, so this should show me, so this if statement should print if my allocation did not go well. So now that I have my my memory allocated, my device pointer allocated on my CUDA, I should be getting ready to invoke my kernel. To do that, I'm going to have to create or call a my kernel, my GPU kernel. Remember, from calling the GPU kernel, you pass two attributes to it, two variables that specifies your parallelization. In my case, I said I want exactly the same number of blocks and the number of pixels I have, 1 pixel per block, and then I would use 1 thread in each block. So I'm going to create a dim3 structure, and I'm going to call it grid, which is going to be dim times dim. Remember, dim being the size of my pixel, of my image rows and columns. So this basically creates a grid of blocks per pixel. And then I'm going to call my GPU kernel with these many blocks and 1 thread per block. And then I'm going to pass to this the device pointer, which was the value or the data pointer to the memory I allocated on my device. So then what's going to happen here is on line 154, it's going to invoke the kernel for dim times dim, basically the size of the image, number of kernels, and it will pass the device pointer to these kernels to calculate. And then the GPU kernel will take the unsigned char pointer and calculate the x and y locations for each kernel associated with the pixel, calculate the Julius value of that pixel, and write it into the data pointer. The last piece of the operation is to transfer this data from GPU back to CPU and store it into the data pointer of my image. So I'm going to basically do that inside of my function, and it's going to be essentially on line 162. So I'm going to replace line 162 with the transfer of my data. So again, I'm going to use the error to see whether the CUDA memcopy worked or not, and then use CUDA memcopy, and then transfer the data to my image.data from the div pointer. And how many do I need? It's going to be my image.columns times my image.rows times size of uchar. And then I'm going to do from CUDA mem copy device to host. And this transfers the data from my device to host, and then I'm going to show the image. Except that I'm going to test to see if error was not equal to CUDA success. Then I'm going to print f some error happened when transferring from GPU to CPU. Okay, so this is my GPU side code. Again, I'm going to allocate a pointer of type unsigned char to match with my image data pointer. I'm going to allocate how many bytes I need for that data pointer, and that would be the size of my image times the size of data char, which is unsigned char. If successful, I go on, create a grid, which is the dimension of my image, and then invoke that many kernels, that many blocks with one thread per block. And then I pass the data pointer of my global variable, global data, to it to calculate the Julius sets. When I'm done, I'm going to go and create and copy the data from my device to my host, and exactly the size of the data pointer that I need, which is going to be the size of my image times the size of my unsigned char bytes, and then specify that I want to go from device to host, and then I'm going to show my image. Let's compile this. And it did work. And this is my GPU calculation of my Julius set for a 512 by 512 image, and associating each pixel of my image to the threads, basically to each block. Now, there's going to be a problem if I associate an image with the size of 1024 by 1024. Well, actually, no, it did work. but it slowed down a little bit. What if I run it for 2048 times 2048? And that did stop working. And let's see what the problem was. There was some error when transferring the data from GPU to CPU for that large number of threads. Aside from this slight little problem there, it wasn't really quick. And the problem is I associated one thread per block. So basically I have a lot of blocks that I'm running. And remember from what we discussed so far that your GPU basically guarantees you that before each block execution is finished, or before each block is run, the execution of the other blocks on the streaming multiprocessor will have to stop or go through completion. So by creating one block with or by creating blocks that basically have one threads inside of them, I'm not really utilizing my parallelization, especially with this case that I have a map. My operation in itself is fairly straightforward. It's just one-to-one mapping between my input data and my output data, or between my pixel location and the value of that pixel. And this is not really, at this point, the most efficient that I could get out of my programming. The best way to program this is to create a block and then to have each block have a multiple number of threads in them. For example, each block to have 16 by 16 or 32 by 32 threads to be able to do data reuse and essentially to increase our occupancy of our graphics processing unit and streaming multiprocessors, because of the fact that this is a highly parallelizable algorithm. This is basically an embarrassingly parallel algorithm. So we get most and we get more out of our parallelization if we actually implement and our program actually does include within its parallelization specification the number of blocks and the number of grids, or the number of threads in each block, to utilize this parallelization. And that would be a homework assignment for you all to do.